Hello and welcome to episode 14 of Chemistry in 15 Minutes or Less. My name is Audra and this review lesson is on chapters 6 and 7, part 7, Molecular Geometries. Now before we actually get into the molecular geometries, we need to talk about something very important. We need to talk about something called valence shell electron pair repulsion theory, or VSEPR. Basically, this predicts the shape of molecules based on electron pairs being as far apart as possible in bonds. This includes electrons that are in bonds and lone electron pairs. So before we go over molecular geometry, we need to go on about electron pair geometries. So this is our nucleus. We have a couple of different specific ones. We have what's called linear, which is exactly what it sounds like, 180 degrees. Then, next, when we have our nucleus here, we have 1, 2, 3. I know my drawings are messy. With 120 degrees. This is called trigonal planar. Then, when there are 4, it's called tetrahedral. Then when we have 5, it's called trigonal bipyramidal. And then with 6, which is a little crowded down here at the bottom, we have octahedral. Now the other important degree measures that I forgot to put in is in tetrahedral, 109.5. In trigonal bipyramidal, from top to side here is 90, but from these on the sides, here, here, and here as well, are all 120. And in octahedral, all 90 degrees. So these are the ways that electrons will form around depending on how many pairs there are. Now, breaking off of these two right here are either do it or bust. The other ones can be based off of these ones. Now, the molecular geometries are based on these. So we have, off of the tetrahedral structure, just the same tetrahedral structure with 4 electron pairs. This would be something like, say, methane, CH4. There are 4 bond pairs and no lone pairs. It can also be, if this is our model, trigonal pyramidal. Basically, in this, there's a lone pair up here. This would be something like ammonia, which is NH3. Or 2 lone pairs. We have a bent structure. This means that there are 2 lone electron pairs taking the place of these over here. This would be something like water. Just gonna write these in. Now there's going to be a lot more coming off of these ones, so I'm going to leave you just a second and then I'm going to clear the space. Now, coming off of our base, trigonal bipyramidal, which I'll draw really quickly. I know it's hard to see depth with the way I'm badly drawing these, but work with what you got. Now, this can break off into 4 main structures. The same, trigonal bipyramidal, I'm not going to draw it again. This is something like phosphorus pentafluoride, 5 bond pairs, no lone pairs. When you get 1 lone pair, you get a seesaw structure. Where you've got a pair over here, and this would be something like sulfur tetrafluoride, my bad. Can also go into T-shaped, which, as you're figuring out the pattern, would have 2 lone pairs. This would be something like chlorine trifluoride, or even possibly going into a linear structure, which would be something like xenon difluoride. You have 3 lone electron pairs, all coming off, taking the place of these, that are technically in a bond in this one. Our final molecular geometry we'll talk about is based off of the octahedral structure. Now this breaks into 3 main structures. Octahedral, which is the same. Just put an example. SF6. Now, if you have 1 lone pair, you have what's called square pyramidal, which looks a little something like this. Bromine, 5 fluorines. Or square planar, but there's 2 lone pairs. Now before we close out, we need to quickly talk about something called hybridization theory. Hybridization theory is basically the way you explain the orbital notation of something that would have a tetrahedral structure with 4 bonds, like for example, carbon. Let me quickly draw the gas notation. Now this is our good old friend carbon. Now in order for this to have 4 bonds, you would notice that you draw it like this. At least as far as the last 2 sublevels go. And you'll notice that there's only 3 spots for it to bond without having to pair up over here. Now, what happens is it hybridizes. Whoops. That should be A3. What that does then is brings all of these to the same level and lets them all stay open. That way you can make 1, 2, 3, 4 bonds, which is what's essential to life. And with that, this should conclude episode 14 of Chemistry in 15 minutes or less. Feel free to leave questions or suggestions in the comments below, and be sure to follow the in-video links, check out the playlist, or head over to my channel for more videos on chemistry review. As always, I hope this helps, and have a great day.